In this video, we're going to talk about buffers and acid deposition. So with buffers, what that is a solution that resists change to pH when small amounts of acid or base are added to it. So a buffer solution is composed of a weak acid with its conjugate base. So there's many places in which you're going to find buffers. One example of this would be in our bodies. So specifically in our cells, we have a buffer solution of dihydrogen phosphate. So this negative, since it's a charge, it should be superscript. And then hydrogen phosphate. So that 2- should also be superscript there. Okay, and another example of a buffer system would be in our blood. So we have carbonic acid and hydrogen carbonate as the buffer system in our blood. This negative sign should also be superscript. Now, the interesting thing about our bodies is that our bodies function within a very narrow range of pH. So for our blood, typically blood is at a pH of about 7.4. Now, if the pH of your blood decreases, so let's say it goes down to 7.35, so that's a difference of 0.05. Anywhere below 7.35, you're gonna get a condition called acidosis. And if you keep on going too far to the acidic side, then what happens is your organs can no longer function because it's not at the optimal pH range for them to function. And again, if your blood gets too acidic, your organs shut down, and then that's going to obviously cause death. Meanwhile, on the other side here, at a pH of 7.45 and above, so if your blood gets too basic, you get a condition called alkalosis. Now, if your blood pH keeps on going further and further up, then your blood will be too basic for your organs to function, and they will start to shut down, and then that will end up in death. Okay, but this isn't a usual concern because the buffer system in our blood, the carbonic acid with hydrogen carbonate, that is really good at keeping our pH of our blood within this normal range between 7.35 and 7.45. Okay, so if you're wondering, well, what could possibly cause a condition such as acidosis? Well, it could even come down to something like if your breathing slows and carbon dioxide builds up in your body and it gets dissolved in your blood, reacts with the water that's in your blood, which would create carbonic acid. And if too much of that carbonic acid is present, then your blood will get more and more acidic, right? So with situations where your breathing is slowing, that could be a situation such as a drug overdose. With alkalosis, there's a variety of ways that a condition such as that could happen, but one such way could be that there's not enough carbon dioxide present in your body, or it could be caused just because you've eaten too many antacids, so something like Tums. If you've eaten too much of that, that can actually increase your blood pH. Okay, so there are a variety of ways in which you can get these conditions of acidosis and alkalosis, but we do have a very efficient buffer in our blood to make sure that that typically doesn't happen. Now, buffers, they typically contain two species, okay, and each have their own individual jobs. So one substance is going to be a weak acid, which is going to be reacting with any base that you add to the buffer solution. And the other one is going to be a weak base, which deals with any acid that gets added to the solution. So, for example, a typical buffer solution might be a solution of acetic acid and sodium acetate as shown. So here they've written it twice. The only difference is for this one. So for this they have sodium acetate. However, over here they already have it dissociated and they're only focusing on what is acting as the weak base. Okay, so this one is a little bit more accurate as to show you what is the weak acid and the weak base that is resisting any changes to pH. It's not to say that what's written over here is incorrect. You just got to be mindful that if you're given an ionic compound, you need to make sure that if it is soluble in water, which this is, then you need to be dissociating it to figure out what the conjugate base or what the weak base is going to be. Okay, so how buffers resist changes to pH is through the following. So let's say we add a strong acid to this buffer solution. Okay, so what's going to happen is we have hydronium ions being acid, so this is coming from the strong acid. And so the weak base is going to react with the hydronium ions coming from the strong acid in order to create the weak acid and water. Okay? And since we have the creation of a weak acid, that's really not going to change the pH of the solution very much. Okay, and that's assuming you're only adding a small amount of strong acid to the buffer solution. If you add too much strong acid or strong base to a buffer solution, then eventually it can only resist pH changes so much before it hits its buffering capacity and it is unable to maintain the pH of the solution. Okay. And we do talk about that a little bit lower down in this page. Okay, but moving on to what happens when a strong base is added to solution. So the hydroxide ions, which come from the strong base, they react with the weak acid in the buffer solution to create a weak base and water. Okay, so again, because this is a weak base, it's really not going to change the pH all that much. Okay, but the main idea here, so that's from the strong base. The main idea here is that the strong acid is going to react with the weak base from the buffer, and the strong base, so the hydroxide ions from the strong base, are going to react with the weak acid in the buffer solution in order to prevent that change or to resist changes in pH. So let's look at our first example here. What would occur to the buffer sodium hydrogen carbonate and sodium carbonate in the presence of a strong acid and a strong base? Okay, So first of all, because we've been given two ionic compounds, which we're told are aqueous so they can dissolve in water, that means we need to dissociate both of these. So what that's going to look like, remember dissociation reactions, you're just splitting it apart into the cations and anions that make up your compound. So you should only ever get two products. So here we've got our cation and our anion. Okay, so typically you're only going to get those two products, the cation and the anion. If you are breaking up an ionic compound for a dissociation equation into more than two products, then you're not doing it correctly. Okay, for sodium carbonate, again, we're just breaking it up into the cations and anions. And we're going to make sure this is balanced. The first equation was already balanced. Okay, so what that means is what is making up or what's doing the heavy lifting in the buffering solution are going to be these guys. So metal ions, remember, they are neutral. Okay, you're not going to find them anywhere in your data booklet on page 8 and 9 because they are neutral and they're not a conjugate base of a strong acid. Okay, so that's why I already know off the top of my head, metal ions, they're neutral. We're not going to worry about them doing anything in our buffering solution. Okay, but what we are going to focus on is hydrogen carbonate and carbonate ions, because those you will find on page 8 and 9 of your table there. Okay, so the compounds doing the actual work will be hydrogen carbonate and carbonate ions. Okay, so what's going to happen in the presence of a strong acid? So remember, strong acids, the quickest reaction that's going to happen is between the strong acid and water, just because there's lots of water present, and that's going to produce hydronium ions. So that's why I'm going to start off with hydronium ions. And because this is an acid, what deals with the acid is going to be the weak base in our buffer solution. So if I look at what we're working with here and find them in this table here, so let's clean it up just a little bit here. And let's just find where this is. So I'm seeing hydrogen carbonate right here, as well as here. And then I've already got my carbonate ions circled right there. Okay, so since we're adding an acid, we know that our weak base is going to come into play here. However, it kind of looks like we have two weak bases. The hydrogen carbonate ions could act as a base, same with the carbonate ions. Okay, so for this, we always want to pick the stronger of the two bases in order for figuring out what's going to react with our acid. So remember, to figure out what is your strongest base, you're picking what is closer to the bottom right-hand corner, so that's going to be our carbonate ions. Okay. So what's going to be happening here is our acid is going to transfer one proton over to our base. So if I imagine hydronium with one less hydrogen in it, that's going to give me water. and then the carbonate ions with one more hydrogen in it. That's going to give me hydrogen carbonate with a 1- charge. Okay, so that's what would happen in the presence of a strong acid for our buffering solution. Now, in the presence of a strong base is always going to produce hydroxide ions. And what's going to react with our strong base is going to be the acidic component of our buffer. So, since we use the carbonate ions to act as our base, then that means hydrogen carbonate, even though it could act as an acid or a base, in this case it is going to act as our acid. But another reason why is because we always want to use our strongest acid to react with our base, and in this case, because hydrogen carbonate is the only acid present here, that's why it's going to be acting as our acid. Okay, so remember acid, A for away, so the hydrogen gets donated from our acid to our base. So then we're producing, so hydroxide with one extra hydrogen in it is water. And then hydrogen carbonate with one less, hydrogen carbonate ions with one less hydrogen is just going to give us carbonate ions. Okay, next example here. We're asked to place the following solutions in order from lowest pH to highest pH. So lowest pH would be like the most acidic one. Highest pH would be the most basic one. And all of these solutions have the same concentration. Okay, so the reason why they specified everything has the same concentration is because pH, or how acidic or basic something is different than how concentrated something is. So I got to make some adjustments here because some of these should be superscript for the charges. So we'll just do that very quickly. Okay. So figuring out what is the most acidic acidic solution here, we can use our data booklet. Okay, so we had carbonate ions, carbonic acid, hydrogen carbonate ions, and then a solution of hydrogen carbonate with carbonate ions, and then a solution with carbonic acid and hydrogen carbonate ions. Okay, so the most acidic one, if we look at our data booklet, let's just go through and circle our chemical species here. Okay, so we already have the carbonate ions circled. Carbonic acid, we are going to find that. Let's see, right there. Okay, now we also had some carbonate ions, which I already have circled here, and I think that's everything. Okay, so looking at what we have circled here, and again, to figure out your strongest acid, you're starting with your finger up here, and then you just scroll down until you hit the first acid that you have listed. So in this case, that's going to be carbonic acid. So what that means is our solution that just has carbonic acid in it, that's going to be the most acidic one. So I'm going to rate that one as the first one. Okay, so we'll just write little placeholders for our answers here, and I'm going to write 2 for for carbonic acid. I'm going to write over here, lowest pH, so most acidic. Versus over here is going to be highest pH. Okay, so looking at the rest of our options here, the next solution that's going to be the most acidic, or the second most acidic, is going to be the one that's got carbonic acid mixed in with its conjugate base. So that's going to be option number 5. Okay, so the reason being is because we don't have just purely carbonic acid, but we still have 2 substances that are acidic. Okay, although this one, so hydrogen carbonate ions, it could act as an acid or a base, but because it's paired with an acid, this solution will be like the second most acidic one. Not as acidic as carbonic acid, but still acidic enough. Okay, now for the next one here, that's going to be just pure hydrogen carbonate ions. So HCO3, 1 minus. Okay, so basically you could think of this as kind of like a spectrum where we gradually lower the amount of hydrogens, because the less hydrogens you have, the less acidic something's going to be. Or you could think of it the other way, the more hydrogens that compounds have, the more acidic that they're going to be for the case of buffer solutions. Okay, so with that in mind here, the next solution is going to be solution number 4, because we've got that mix of hydrogen carbonate ions with carbonate ions. Okay, so the hydrogen carbonate ions, they could act as an acid or a base, but carbonate ions can only act as a base. And then last but not least, we have our carbonate ions, which will be the most basic ones here. Okay, so again, just to notice, like across the board here, the solution with the lowest pH from all of these choices, that was the one that had the most hydrogens in a compound here. Whereas the next most acidic solution had a mix of our carbonic acid with hydrogen carbonate, which could act both as an acid or a base. Our species in the middle here is just pure hydrogen carbonate. It could either act as an acid or a base, either or. It's amphiproduct. However, for the next solution, that's going to have a mix of hydrogen carbonate with carbonate ions, and then last but not least, carbonate ions that can only act as a base, or a weak base, sorry. So just as a recap, a buffer is a solution that contains a weak acid and its conjugate base. So let's just add in that it is a weak acid. And on a graph, the buffering region is where the acid, the weak acid, and the conjugate base are both present. Okay, so you can identify these buffering regions where you have these flat sections of your titration curve or your pH curve. The only flat section that's not going to be a buffering area is going to be the last flat section, and that's just because all of the buffering compounds have been used up, like they can't act any further. Okay. For buffering capacity, I mentioned that earlier. That's the limit of the ability of a buffer to maintain a pH level. So if I drew just a little sketch of a titration curve, okay, so here we would call that the buffering area. Now here, where we have this very large jump in pH, that would be when the buffer has reached its buffering capacity. Okay, so basically what's happened here is we've added so much base that the buffer can no longer resist changes to pH, and that's why we get this giant jump in pH. Okay. So when it says these areas, we're meaning buffering areas. Okay, more examples of buffers. So which of the following solutions could act as a buffer system? So let's take a look at what we've been given. So we've been given potassium dihydrogen phosphate and phosphoric acid. So remember, if you're given an ionic compound that's soluble in water, you're going to want to dissociate it. So what's doing the heavy lifting here would be H2PO4 with a 1- charge. And we've got phosphoric acid. Okay, so what we're going to want to do is we're going to want to check our data booklet and just see, are both of these, or do we have one weak acid and one weak base? Okay, so I'm going to clean up this page a little bit. Okay, so I'm seeing phosphoric acid right here, and we've got dihydrogen phosphate right there. So we've got a weak acid, a weak base, so yep, that could be a buffering system. Okay, now let's look at the other ones. We've got hydrochloric acid, which is a strong acid. Oh. All right, now let's look at the other ones. We have hydrochloric acid, which is a strong acid. So remember, we only want weak acids, weak bases. Because we have a strong acid, this one's already out of the running. With the next one, we have KClO4 and HClO4. Well, if we look at our data booklet, okay, remember, anything in the acid column above this gray hydronium line, these are all strong acids. So that's why I was saying hydrochloric acid is a strong acid. This is how I know. Okay, but we also have perchloric acid. So because this is perchloric acid, it's a strong acid. So this cannot be a buffering system because it has strong acid. So we're going to say not buffers, because strong acid's present. Okay, with the last one here, we have hydroxide ions. So hydroxide ions, those are going to act as a strong base. And remember, for buffers, you only make them up with weak acids and weak bases. Okay, so that puts that out of the running. So our answer is A, because that's the only thing or only solution that's made out of a weak acid and a weak base. For the next question, we have a beaker that contains 100 milliliters of a buffer comprised of 0.1 mole per liter sodium acetate and 0.1 mole per liter acetic acid. A small amount of sodium hydroxide is added to this buffer. The net ionic equation represents what occurs is what? Okay, So I'm going to want to focus on what is actually doing the heavy lifting in this buffer solution. So because we've been given an ionic compound, we're going to want to dissociate it into its cation and anion. If I look at my table here and find acetic acid, the acetate ion is CH3COO. So what that means for us is that the CH3COO with a 1- charge, that's the anion, and sodium is the cation. Okay, now sodium, we know that's neutral because it's a metal ion, so it's not going to do anything. So what's actually acting as our weak base is the acetate ion. And then the weak acid is acetic acid. Okay, so now that we have that figured out, we're seeing, okay, we have a strong base being added. How I know it's a strong base is because any metal with hydroxide, that is going to be a strong base forever and always. Okay, now again, because we have an ionic compound, you're going to want to dissociate it to see what's actually acting here. Okay, so this is going to dissociate into sodium ions and hydroxide ions. And remember, sodium ions, they are neutral, so they're not going to do anything. So what is going to do something is the hydroxide ions. Okay, so hydroxide ions, we know it's a very strong base. So that means our base is going to react with our acidic compound. So that's going to be the acetic acid here. Okay. So what that's going to look like, let's see if we can omit any here. So we're going to omit D because they didn't dissociate sodium hydroxide. And we're going to omit A because they have acetic acid reacting with water. Now between B and C, I would pick C because it has the acetic acid reacting with the hydroxide ions. Okay, whereas B has our weak base reacting with our hydroxide ions, which are basic. So a base reacting with a base doesn't make sense. Acids will react with bases, bases will react with acids, okay? Okay, moving on to acid deposition. Okay, so acid deposition is due to carbon dioxide in the atmosphere. Rainwater, it makes the rainwater just naturally slightly acidic. However, where the problem comes in is where we have gases that are produced by emissions from human activities. So I'm going to say caused by gases. So read that as emissions produced by human activity can take that already naturally slightly acidic rainwater and make it very acidic. Okay, so where we're going to have compounds that are produced by human activity that contribute to acidic rainwater, that's going to come from compounds such as sulfur oxides, nitrogen oxides, and carbon oxide. So these are the main actors here. So sulfur oxides are going to react with water to form sulfurous acid. Nitrogen oxides are going to react with water to produce nitrous acid, and carbon oxides are going to react with water to form carbonic acid. So all of these are reacting with the water in the atmosphere to produce acid rain. And where these sulfur oxides, nitrogen oxides, and carbon oxides are coming from are from a variety of different sources, such as burning coal in power plants that have where the coal has lots of sulfur in it. Another place where you're going to find these gases being produced is when humans are refining or smelting metal ore. And then last but not least, fossil fuel combustion. So when you are running your car, that produces carbon dioxide, which mixes with the water in the air to produce carbonic acid. Okay, so why do we care about acidic rain? Well, because it has lots of different effects on the environment. So acid rain can contribute to the death of vegetation, and how it does this is because once acid rain gets into the soil, it's going to change the soil pH, which inhibits plant growth and causes defoliation of leaves in plants. So all defoliation is just a plant losing its leaves. Okay, but the main idea here is if the soil gets too acidic, just like us, plants can only thrive in a certain pH range. And if the soil gets too acidic, plants can no longer thrive and therefore they die off. Another thing that acid rain does, so when it gets into the soil, the acidic components in acid rain, what it does is it breaks down minerals in the soil, which allows them to be carried off before plants are able to absorb those nutrients. So that's why it's saying washing away of soil nutrients. It's because the acidic compounds or the acid rain is breaking down minerals and causing it to wash away before plants can absorb it. Acid rain can cause the corrosion of metals, so things like automobile coatings or building materials. Acid rain wears those down. You can also get increased rates of asthma and bronchitis, so that's mostly because of pollution from all of these sources of emissions. Okay, and acid rain can also cause the reduction in fish populations in lakes. Just because, again, fish like us, they live or they thrive in a certain pH range. If the pH of the lake or whatever body of water they're in gets outside of their optimal pH range, they can die off. Okay, over here it does say that when bodies of water get too acidic, that can also cause weakening of shells in animals such as crustaceans and insects. Okay, so with these photos down here, this is just demonstrating how acid rain can wear down on stonework that's made out of calcium carbonate. So over here we have a picture of a statue that was taken in 1908, and then that same statue 60 years later looked like that due to acid rain. So what's happening here is the acid rain is wearing down the statue. So how that's happening is because calcium carbonate, that is a basic substance, and when the acidic rain comes down and washes over top of the statue, we have acid base or a neutralization reaction happening, and due to that reaction happening, it causes the calcium carbonate to erode. Now, the soil found in Alberta just naturally contains calcium carbonate as well as magnesium carbonate, so both of these are weak bases, which acts as the Earth's buffer to neutralize acid rain. Okay, so the reaction that's happening here, so there's the carbonate ions coming from either calcium carbonate or magnesium carbonate, and it's reacting with the acid rain to produce hydrogen carbonate and water. Now, there are a few ways in which we can reduce acid deposition. Okay, we can use scrubbers in coal-burning power plants. So what this does is this removes sulfur dioxide from combustion gases. So it basically prevents these sulfur oxides from being formed, and therefore the sulfurous acid can't be formed if there's a reduced amount of sulfur oxide being pumped into the atmosphere here. Okay, catalytic converters that are found in cars or just any vehicle, that can also help to reduce nitrogen oxides, carbon monoxide, and hydrocarbons. And it does that by converting them into nitrogen gas, carbon dioxide gas, and water vapor. Liming is a strategy that involves adding calcium carbonate, which is also known as limestone, or magnesium carbonate to lakes that have granite beds to help neutralize the acidified water so that all of the aquatic life doesn't die off. So lakes with granite beds, where you're going to find those are mostly in Ontario. And some other ways to reduce the amount of like oxides, so such as sulfur oxides, nitrogen oxides, and carbon oxides being emitted into the air would be solutions such as using fuel cell cars, so those don't produce carbon dioxide gas, or if you absolutely do have to drive a car, you could carpool with somebody else to reduce emissions, or you could walk, bike, use public transport. Using emission tests, so basically what that is having your vehicle tested so that it complies with environmental laws, so that it's not producing an excess amount of emissions, which contributes to acid deposition. You can have alternate energy sources. So what that means is you could use wind energy from wind farms instead of getting energy from coal-burning power plants. So that eliminates the emissions there. For water, that'd be like hydroelectricity. So you're getting electricity or you're getting energy from hydroelectric dams. Or another one using water could be using tidal energy. So what's happening here is you have these like huge turbines in the water, and when the tide comes in, these turbines get turned, which produces kinetic energy, which gets converted into electricity and doesn't produce any emissions. Okay, another alternative energy source could be something like solar energy, geothermal energy, and also nuclear energy. So recycling can also decrease the amount of emissions that we're pumping into the atmosphere, as well as improved insulation. So with improved insulation, that could be something like with your window panes. So some really old window panes, they might be only made up of one pane of glass. However, more modern ones are made up of either 2 or 3 panes of glass. And in between these panes of glass here, so in between your panes of glass and your window, there is a gas that could be either argon gas or krypton gas. So both gases are quite dense and they're quite terrible at transferring heat. So what that means is when something's terrible at transferring heat, they're really good at insulating things. Okay, so if you have argon or krypton gas in between 2 panes of glass in your window, then that's going to reduce the amount of heat lost through the window. Okay, so there are some practice questions here, but what I wanted to draw your attention to just at the end of this booklet was some summaries about strong and weak acids and bases. Okay, so make sure you read through this because there's also a summary of weak acid and base calculations. Okay, so this goes over some of the material that was covered throughout this booklet here. Okay, and then beyond that, there is some sample diploma questions and some more information just with the difference between acid strength and concentration, which I very briefly mentioned earlier in the lesson. So concentration has to do with the amount of solute compared to the amount of solvent in a solution, whereas acid strength refers to just how much an acid is going to ionize in solution. Okay, so concentration and strength of an acid, they are two different concepts there. So make sure to read through this on your own time here.